Redox processes, oxidation and reduction. The essential idea: redox reactions play a key role in many chemical and biochemical processes. The nature of science, how evidence is used, changes in the definition of oxidation and reduction from one involving specific elements, oxygen and hydrogen, to one involving electron transfer, to one invoking oxidation numbers, is a good example of the way scientists broaden similarities to general principles. Theory of knowledge. Chemistry has developed a systematic language that has resulted in older names becoming obsolete. What has been lost and gained in this process? Have a think about that. Here's some examples of redox reactions. They're very common. They occur within batteries or when nails rusting, an apple browning, fireworks are examples of oxidation reactions. So what exactly are these things? Oxidation and reduction, also known as redox reactions. These are reactions that involve a transfer of electrons from one reactant to another. So redox reactions always have two half reactions. The oxidation reaction is the loss of electrons, and the reduction reaction is gain of electrons. These half reactions are always paired together or coupled. Electrons move from the oxidation half reaction to the reduction half reaction. So let's have a look at oxidation reaction of alcohols. Alcohols are covalent compounds, which means they'll usually not form ions when they lose electrons, but electrons will shift away from the atom that is oxidized. The two signs that an organic compound has undergone oxidation are: the compound gains oxygen atoms and the compound loses hydrogen atoms. Here and here you can see that this first step, oxygen, there's one atom here, and then there's two atoms in this molecule, so it's gained an oxygen. And you can see that the compound also loses hydrogen atoms. You've got 6 hydrogens here and only 4 over here. For example, we've got primary alcohols can undergo 2 successive oxidation steps. You go from a primary alcohol to an aldehyde to a carboxylic acid. You've got this primary alcohol here, ethanol, and it's oxidized to give us ethanal, which then can be further oxidized to give us the carboxylic acid. These oxygens here are provided by an oxidizing agent, in this case acidified dichromate. 2 signs that an organic compound has undergone reduction are: the compound gains hydrogen atoms and the compound loses oxygen atoms. Here you can see this molecule has 4 hydrogen atoms, and then here it's been reduced, and so it has 6 hydrogen atoms. And here we've got 2 oxygen atoms, and after the reaction, only 1 oxygen atom. So it would be the opposite way of what we just looked at. You've got the carboxylic acid being reduced to give an aldehyde, and then further reduced to give a primary alcohol. And the reducing agent, or one reducing agent we could use, would be lithium aluminium hydride in anhydrous conditions. You can't have any water around. Let's have a look at this a bit closer. We've got the carboxylic acid there going to an aldehyde to a primary alcohol. You've got ethanoic acid being reduced to ethanol, being further reduced to ethanol. Let's look at the structures. You've got the carboxylic acid group here being reduced to the aldehyde group, and then we've got an alcohol here. And like I said, we've got the lithium aluminium hydride, and it's got to be in dry ether, anhydrous conditions. You don't want any water there, or it won't work. Okay, oxidation numbers. An oxidation number, or oxidation state, are a way to keep track of how many electrons an atom gains or loses in a redox reaction. Oxidation numbers have two parts. They've got a positive or negative sign, and they've got a number after the positive or negative sign. If it's got a positive sign, we know that electrons move away from this atom. If it's got a negative sign, we know electrons move towards the atom. The number tells us how many electrons move. And it's very important that the oxidation numbers, the sign is always before the number. Okay, and you can see how important that is because there's this nice fancy star there emphasizing how important it is. We assign oxidation numbers to atoms of each element in a substance. Let's have a look at carbon dioxide here. The carbons has an oxidation number of +4. The oxygen has an oxidation number of -2. And there's two oxygens, so altogether it would be -4. And you can see it balances out, so there'll be no charge. Aluminium sulfide. Aluminium has a charge of +3. Sulfur, an oxidation number of -2. There's 3 of them, so it'd be -6. There's 2 aluminiums, so this would be +6. Potassium sulfate. See, potassium has an oxidation state of +1, sulfur +6, oxygen -2. And again, that would balance out if you do the math. We've got ethanol, carbon, oxidation state of -1, hydrogen +1, oxygen -2. And in diatomic oxygen here, you can see the oxidation state is 0. So what are the rules? What are the rules? How do we know these things? Well, there's a whole bunch of rules, as you could probably guess. For pure elements, the oxidation number is 0. So all of the diatomic molecules we've grown to love and standalone pure elements have an oxidation number of 0. Monoatomic ions such as sodium, potassium, magnesium, iron, etc. And the halides and oxygen and sulfur as well. The oxidation number is just the same as the charge. So we've got a charge of +1 on a sodium ion, so the oxidation number is +1. We've got a charge of 2+ on magnesium, oxidation number would be +2, etc. For hydrogen, it can have an oxidation number of +1 or -1. It's +1 in virtually all compounds except for the hydrides, the metal hydrides, where the oxidation number of hydrogen is then -1. Oxygen similarly has 2 rules. Ordinarily, in most compounds, it's -2, but in peroxides, it's -1. For the group 1 and 2 metals in a compound, group 1 metals have an oxidation number of +1, group 2 oxidation number of +2, so that's nice and easy to remember. Similarly, the group 7 compounds, halogens in a binary compound, the oxidation number is -1. Okay. Any other element in a compound, how do we do this? Well, any other element, except for those noted in rules 1 and 6, can have variable oxidation numbers, and we've got to calculate it. Okay. Oxidation number of the compound, if it doesn't have a charge, if it's not an ion, will equal 0. Okay, and you can use the oxidation state of the known elements. Say, for example, here we know oxygen from our rules will be -2, and we've got 3 of them, so it'll be 3 times -2. We know that that has to balance, the sulfur needs to balance that to give us an overall oxidation state of 0. The oxidation states will cancel out, and so X must be +6. Let's have a look at ethene. We've got 4 hydrogens, and it's not a metal hydride, so we know it's +1. We've got 4 of them, so we've got 4 here. And we've got 2 carbons, and the oxidation state of carbon is X here. So you can do the maths, and X is -2. Here, we know that sodium from our rules has an oxidation state of +1. We know that oxygen from our rules has an oxidation state of -2, and there's 3 of them. And so we can calculate the oxidation state X of bromine to be +5. Here we've got 2 oxygens. Oxygen has an oxidation state of -2. There's 2 of them. and so we can calculate the oxidation state X of chlorine here will be +4. Here we've got propane, and we've got 8 hydrogens, oxidation state of +1 each. That gives us 8. We've got 3 carbons with oxidation state of X, so you can do the math, and it's going to give us -8/3. In polyatomic ions, it's very similar to what we've just done, but this time the oxidation numbers will add to equal the charge on the ion. So in sulfite, we've got -2 here. Okay, the charge is 2-, so the overall oxidation state will be -2. So we just do the maths again. We know oxygen has an oxidation state of -2. There's 3 of them. So to balance it, to give us -2, X must equal +4. So sulfur has an oxidation of +4. Here we've got a charge of -1. So the overall oxidation state is -1. We've got 4 oxygens with an oxidation state of -2 to do the math, and the oxidation state of chlorine will be +7. Here in the dichromate we've got 7 oxygens with an oxidation of -2. We've got 2 chromiums, and the overall oxidation state is -2, giving us an oxidation state of +6 for the chromium. In the ammonium ion, we've got 4 hydrogens, each is +1, and so to balance that and give us +1, we need an oxidation state of -3 on the nitrogen. And here we've got 4 oxygens, each with a -2, and so the oxidation state of phosphorus, to give us an overall -3, must be +5. Okay, you can press pause and have a go at these. Splendid. Well done on getting all those correct. Okay, we're just going to have a look at naming polyatomic ions. You will see in a lot of the books that we use and on YouTube videos, etc., sulfite, bromate, perbromate, bromite ions, hypobromite. These are the old system of naming, okay? The new system of naming is far more straightforward, okay? You just put the stem of the first element, so if it's sulfur, and then you put 8 sulfate, bromine, so bromate, okay? And then you just write the oxidation number of the first element. So you'd calculate the oxidation state of sulfur, and in this case it's +6, so you'd have sulfate 6 ion. For this bromate ion, the oxidation state is +5, bromate 5 ion, etc. It's very straightforward, and it's a simple rule to follow. Okay, can you have a go at this? Press pause and have a go. Well done on getting all of those correct. Excellent work. Oh, someone just shut the door. Okay. We're going to use oxidation numbers to identify oxidation and reduction reactions. Remember, reduction reactions is the gain of electrons. And so, there's a decrease in oxidation number. Here you can see magnesium has an oxidation state of +2, and after the reduction reaction, where it's gained electrons, it has an oxidation state of 0. There's a decrease in the oxidation number. Similarly here, iron had an oxidation state of 3+, and it's gone down to 2 because it's gained an electron. Oxidation reactions are the loss of electrons, or an increase in oxidation number. Here, sulfur had an oxidation number of -2, and it's increased to 0, and it's lost electrons. And here we've got iron with an increase in oxidation number from 0 to +2, and again it's lost these electrons. Okay, we're going to show using oxidation numbers that the conversion of ethanol into ethanal and then ethanoic acid are oxidation reactions, which we saw on a previous slide. First things first, you can rewrite the formulas and assign oxidation numbers. Okay, so rewrite it and then add the oxidation numbers above. You can then look at these oxidation numbers and see which one's changing. Quite clearly, the oxidation numbers on hydrogen and oxygen remain the same, but the oxidation numbers on the carbon in the alcohol, the aldehyde, and the ethanoic acid are changing. The oxidation number is increasing. And so, the oxidation number for carbon increases from -2 to -1 to 0, therefore it is oxidation. Right, we're going to deduce and explain that the substance is reduced and oxidized in the following reaction. So first of all, assign oxidation numbers and then look to see what's changing. You can see that sulfur dioxide is oxidized because the oxidation number of sulfur increases from +4 to +6. It's gone from 4 to 6. And oxygen here is reduced because the oxidation number of oxygen decreases from 0 down to -2. So, definitions. An oxidizing agent is the reactant that accepts electrons, the reactant that causes another substance to be oxidized, and the reactant that is reduced, or the oxidation number decreases. A reducing agent is the reactant that supplies electrons, the reactant that causes another substance to be reduced, and the reactant that is oxidized, or the oxidation number increases. Let's have a look at this one here. So we've got magnesium increasing in oxidation number from 0 to +2. And we've got oxygen decreasing in oxidation number from 0 to -2. So if the oxidation number is increasing, magnesium is oxidized, and if the oxygen is decreasing, oxygen is reduced. Therefore, if magnesium is being oxidized, it must be the reducing agent, and if oxygen is being reduced, it must be the oxidizing agent. So, some common oxidizing agents. We're going to show that the reactant in blue acts as an oxidizing agent. Okay, for sulfur dioxide, there's oxidation of iron and the reaction between nitrogen and oxygen. Then we will look at an ethanol to carboxylic acid. Another rule that we can kind of should bear in mind for the common oxidizing agents is that halogens have a very high electronegativity value, and therefore they easily remove electrons from other substances, so they're common oxidizing agent. So oxygen's easy to remember, right? Because it's called oxygen and it's an oxidizing agent. Dichromate ion is very common, and often you see that the oxygen is written like we saw earlier, just inside the little square like that, and the halogens which have high electronegativity values. Common reducing agents, obviously hydrogen, which we saw in previous slides, and carbon is also quite a common reducing agent. So let's look at a bit more detail. Here you can see that the oxygen is going from 0 to -2 here in the sulfur dioxide reaction. Similarly, oxygen is going from 0 to -2 in the reaction with iron and in the reaction with nitrogen too. And so the oxidation number of oxygen decreases from 0 to -2 in all three reactions. Therefore, the oxygen is reduced. Therefore, the oxygen is the oxidizing agent. With the dichromate ion, you've got chromium with an oxidation number of +6 going to an oxidation number of +3. So the oxidation number of chromium decreases from +6 to +3, therefore chromium is reduced, therefore the dichromate is the oxidizing agent. Let's look at these reducing agents. We can see here that hydrogen has gone from 0 to +1, so the oxidation number of hydrogen increases. Therefore hydrogen is oxidized, therefore the hydrogen molecule is the reducing agent. Here the oxidation number of carbon increases from 0 to +2, therefore the carbon is oxidized, therefore carbon is the reducing agent. Okay, you can press pause again and identify the oxidizing and reducing agents in these reactions and give a reason. Press pause and have a go at all four. Okay, we can see here that potassium is increasing in oxidation number, bromine is decreasing. So if potassium is increasing, it is being oxidized, and therefore it must be the reducing agent. If bromine is decreasing in oxidation number, it's being reduced, therefore it is the oxidizing agent. Here we've got silver, and the oxidation number increases, therefore it's being oxidized, so it must be the reducing agent. We've got hydrogen sulfide. You can see the hydrogen's gone from +1 down to 0, therefore it's being reduced, therefore the H2S must be the oxidizing agent. And the other two, so look, we've got nitrogen decreasing from 0 to -3, so nitrogen is being reduced, so nitrogen must be the oxidizing agent. Here we've got oxidation number of hydrogen increasing from 0 to +1, therefore hydrogen is being oxidized, so it must be the reducing agent. Here we've got carbon in carbon monoxide going from +2 to +4, so carbon is being oxidized, so the carbon monoxide must be the reducing agent. Conversely, the nitrogen is going from +2 down to 0, therefore nitrogen is being reduced, and so the nitrogen monoxide must be the oxidizing agent. And that is the last slide for this presentation. Splendid.